Hello, this is Richard Bennell, and I will be presenting the paper on the economics of offline password cracking. This paper was written by Jeremiah Blocky, Ben Harsha, and Samson Zhu of Purdue University. The authors of this paper created an economic incentive model for cracking compromised hashed passwords. Their determination is to find out at what point does it become financially untenable to continue attempted password cracking. The model, after it was created, was applied to several major password breaches in recent years, including Yahoo, Dropbox, LastPass, and Ashley Madison. The authors present evidence that most of the users' passwords follow a Zipf's law distribution. They argue as author that current password protections by the compromised organizations are insufficient to dissuade offline password cracking from most user passwords. In their introductory section to this paper, the authors stated the goal of, can we quantitatively predict how many user passwords a rational attacker will crack after a breach? In order to do that, an attacker who has stolen a user's password hash value can attempt to crack each user's password offline by comparing the hashes of likely password guesses to the stolen hash value. Because the attacker can check each of these guesses offline, it's no longer possible to lock out the adversary after several incorrect guesses, allowing an offline attacker unlimited attempts, with the limitation only being the cost of computing the hash function. Ideally, the password hashing algorithm should be moderately expensive to compute, so that it's prohibitively expensive for an offline attacker to crack most user passwords. Rational password attacker is economically motivated and will quit guessing once his marginal costs exceed the marginal reward. The author's major contributions from this paper are the development of a decision-theoretic framework to quantify the damage of an offline attack, and given the expected marginal value of each additional cracked password, what will be the value of these cracked passwords? And their framework allows for the setting of diminished returns for each additional cracked password. For example, the first password may be worth $1, and the additional password will be worth a diminished amount past that. They discuss Zipf's law modeling the distribution of the selected user passwords, including 70 million user accounts in the Yahoo password frequency corpus. They locate a finite threshold which characterizes the expected stopping point of attacks. If 1 minus X percentage of passwords follow the Zipf's law distribution, then a rational attacker will attempt to compromise at least that same percentage of passwords. They develop model-independent upper and lower bounds for a fraction of expected passwords to be cracked. And prior to cracking, it's impossible to know whether the percentage of the passwords will conform to Zipf's law. Additionally, they apply the model to a large-scale password breaches using the same password corpus from LastPass, Ashley Madison, Dropbox, and Yahoo. Unless the password value is less than predicted, the rational attacker would attempt to crack 100% of these hashed passwords based on the value of the given password and the marginal cost to attempt to crack these. In the preliminary section of the development of the economic model, the authors asked the following key questions and discussed the following key parameters. How many guesses will the rational adversary attempt? What fraction of the user passwords will the adversary manage to break? How valuable is each individual cracked password to the adversary? And what is the cost to compute the hash value each time they validate a new password guess? The below variables are what they used for the development of the equations at the very bottom of the page. They also discussed the black market values for the hacked passwords prior to the Yahoo breach, ranging from approximately $4 to $30 each, and subsequently have ranged from 70 cents to $1.20, but have been held artificially low due to dishonest behavior, which suggests the value for legitimately cracked passwords may be higher. In the rational adversary section of the economic model development portion of this paper, the authors discuss the following key parameters. The attacker has obtained the list of hash passwords. The hacker knows the password distribution and the corresponding passwords. However, the attacker does not know which password any individual user has selected. They also allow for the availability of diminished returns based on the function described in bullet point 4. There are a number of reasons why an attacker may encounter diminished returns for an additional cracked passwords. First, if the attacker plans to sell the passwords on the black market, then basic economics suggests that an increased supply of cracked passwords is likely to drive down prices. In the case of large breach like Yahoo, which consisted of 500 million passwords, It's conceivable the number of available passwords on the black market might quickly increase by 2 orders of magnitude. Second, the more user accounts that are hacked/actively exploited, the more likely it is the original breach will be detected. If the breach is detected, then an organization can ask or require users to change their passwords or require two-factor authentication, which will reduce the value of each cracked password. However, the cracked passwords arguably still have significant value after the breach is detected for 2 reasons. First, many users will not update their passwords unless they are required to do so. Second, many of the users that do update their passwords may do so in a predictable way. Third, many users will have the same password for other accounts. In modeling the methods the attacker would use to crack a password, a random password is selected from the list of compromised passwords, and an attacker chooses a threshold greater than 0 of the most likely passwords. If the password contained in the list of attacker guesses, the attacker receives a payment of V, select as shown on the previous slide. Regardless of the payment received, the attacker is charged J times K, where J is the index of the correct password from the list of passwords. The authors discuss the rational adversary characteristics and note that the rational adversary is both informed, untargeted, and rational. That means the attacker knows the password distribution and the passwords, but does not know the association between any user and the password. The rational adversary has no knowledge of background information to decrease the password pool, as in he has no information about any specific user within the password list. And he is economically motivated. An attack will stop when the marginal guessed cost exceeds the marginal expected return. They develop the equations on this slide, whereas the rational attacker chooses threshold T, the expected cost per each guess, and the expected return for each guess is displayed. In the interpretation section of the economic model portion of this paper, the authors discuss the value of the entire dataset, as well as the value of any individual password within the dataset. They give the example of 1% of passwords being hacked, with the value of each individual password at $4. They also discuss the marginal cost to increase the guess threshold from T-1 to T, and the marginal reward for the same action, and is presented by the following equations. The authors discuss the limitations of their model in that it does not incorporate a model for the equilibrium of cracked password prices. The model assumes the values for cracked passwords are steady, and therefore the model does not account for competition among attackers. Breaches that are undetected will have minimal competition, whereas public disclosures would increase the number of attackers vying to be the first to crack a password. In extremely competitive settings, for example, a password for a cryptocurrency wallet, only the first attacker to crack the passwords will be rewarded. The model is also intended to show an untargeted, economically motivated attack, where specific user passwords will not have a higher value to the attacker, for example, a celebrity or a politician. Nation-states may place a greater value on cracked passwords for specific users than the open market would, for example, some defense individual. Zipf's law is an empirical law that, given a particular corpus of natural language utterances, the frequency of any word is inversely proportional to its rank in the frequency table. Therefore, the most frequently occurring word will occur approximately twice as often as the second most frequent word, 3 times as often as the third most frequent word. For example, in the English language, the word the is the most frequently used word, followed by and, which occurs approximately 1/2 as frequently as the word the. The Yahoo breach had 70 million hashed passwords, and it fits Zipf's law very closely for passwords occurring more than 5 times in the hashed passwords list. For this paper, the authors were able to gather a large number of compromised passwords from each of the various systems. From Yahoo, they were able to gather 70 million compromised passwords, from Dropbox, nearly 70 million, from Ashley Madison, 40 million, and an unspecified number of passwords from LastPass. However, they do specifically mention the value of these is expected to be higher, as these are master passwords, which would contain additional passwords within the compromised system. The authors then took their economic model and applied it to each of the individual breaches with the following assumptions. They assumed that SHA-256 can be calculated 10 to the 7th times per second. They assumed diminishing returns of 20% per password. They set the initial value for the first cracked password at US 48 cents. And then they found that the rational attacker would continue to crack 100% of passwords for each breach, even given this minimal starting point and diminishing returns at 20% per cracked password. Additionally, they did further black market research and found out that from various locations, password values could range from 48 cents all the way up to US $30 for the initial password. And they built the table of diminished returns at 100% for no diminishing returns, 90% and 80% to show possible marginal value for additional cracked passwords. The authors discuss mitigation techniques to disincentivize an attacker from attempting to crack all passwords in a data set. The current authentication protocols will need approximately 7 seconds per authentication to obfuscate hashed passwords to disincentivize the attackers. This is using the same 10 to the 7th technique for SHA-256. Alternatively to using 7 seconds per authentication attempt, the authors suggest using memory hard techniques, although they don't discuss in detail specifically what they mean by this. They discuss that memory hard algorithms do increase the complexity of the hashing without dramatically increasing the hashing time, and they would increase the marginal cost per cracking attempt, making the minimum value $30 to be economically viable with no diminished returns. The authors also suggest key stretching techniques, such as storing fake hashes on one server and true hashes on another, which would allow a notification of breaches when the false hashes have been detected.